So today, we are diving into a really radical new idea, one that doesn't just try to solve one of the hardest problems in computer science, it actually argues that the problem itself might be an illusion, a kind of ghost created by our obsession with time. Let's get into it.
Look, for over half a century, the P versus NP problem has been this final frontier of computing. But this new paper asks a really disruptive question. What if we've been trying to climb the wrong mountain this whole time?
Okay, so quick refresher. P problems are what we think of as easy for computers. Things they can just solve directly, like finding the absolute shortest route on a map. But NP problems, they're the tricky ones. They can be incredibly hard to solve from scratch, but, and this is the key, if someone gives you a possible answer, it's super easy to check if it's right. It's kind of like the difference between finding the one winning move in a super complex chess game versus just confirming that, yeah, the move someone showed you does in fact lead to checkmate.
And a whole debate, the entire reason P versus NP is a $1 million prize problem, it all boils down to computational time. Does solving one of these monster NP problems fundamentally require a ridiculous, exponential amount of time? Or is there some clever, fast shortcut we just haven't been smart enough to find yet?
This is where the paper proposes what it calls a Copernican shift. I love that phrasing. Instead of trying to build a faster ship to cross the ocean, it's asking, what if we question the ocean itself? It suggests we just remove time from the equation of computation altogether.
And this is where the argument gets really bold. The author isn't just treating this as a computer science problem anymore. No, they're reframing it as a fundamental question of physics, drawing a direct line to how Einstein completely reimagined space and time.
And this, right here, illustrates the new paradigm perfectly. Classical computation, it's like following a recipe, one step after another over time. But this new idea, atemporal computation, is way more like a crystal suddenly forming in a solution. It's a single instantaneous event where the answer just precipitates out of the problem's own structure.
So how in the world does this actually work? Well, it's built around this really key Korean concept called Changbal, and it describes how a totally new kind of machine doesn't compute an answer, but instantly jumps to it.
Now the key here is that Changbal is not about slow, gradual change. It's a sudden, discontinuous leap. Think about the exact moment that water flashes into ice. The system crosses a boundary, and boom, it instantly has a new property. In this case, that new property is solvability. This diagram from the paper just shows it all. I mean, on the left, you've got your classic Turing machine, just chugging along a horizontal timeline, one step after another. But on the right, that's the Changbal Jump Machine. It's a vertical process. All the problem's pieces fall through what's called a jump operator and just collapse into a single atemporal resolution. And this right here, this is the mathematical heart of the whole idea. In this new way of thinking, that barrier between P and NP, it just collapses. The theory captures it in this equation, which basically says that P is the same as NP under a special condition called a jump invariant. What it really means is, once you take time out of the picture, the two problem types become one and the same.
So of course, this leads to a totally new way of measuring how hard a problem is. We're all used to big O notation, which is all about time. Well, this paper proposes O of j, where j stands for the jump. Suddenly, problem complexity isn't a measure of time anymore. It's a simple yes or no question. Can this problem structure be resolved in a single, instantaneous physical jump? That's it.
Okay, I know what you're thinking. This all sounds incredibly theoretical, right? Pure sci-fi. But the paper argues it's not just theory. So how would you actually build a machine that could do this?
Well, the paper lays out a 6-step pipeline. First, you take any problem and you translate it into a standard format the machine can understand. Then you pre-process it with these really powerful math tools like Fourier transforms, basically breaking the problem down into its most fundamental frequencies. From there, that structure is converted into physical signals, like waves, which get fed into the machine. And then the machine performs the single jump, settling into a stable state that gives you a physical true or false answer.
And let's be super clear here. This machine isn't running an algorithm. It's not calculating in any way we'd recognize. It's a physical system that's designed so that its natural state of rest, its lowest energy, its equilibrium, is the answer to the problem. It doesn't find the solution, it becomes the solution.
And this is not just hand-waving. The paper actually grounds this in real-world engineering, proposing some incredibly precise components. We're talking about things like sapphire resonators to handle the signals with perfect clarity, and Josephson junctions to manage the quantum effects you need for the jump. The point is, this is a proposal that's rooted in concrete physics that we can actually work with today.
So if a machine like this were even possible, the implications would be, well, staggering, and they go way beyond just computer science. This is where the paper gets truly profound.
The author very deliberately invokes Oppenheimer and the dawn of the nuclear age. The message could not be clearer. A breakthrough like this isn't just an advance, it's an irreversible shift in our reality, one that carries immense power and immense responsibility.
I mean, just think about what this means. Security and trust would no longer depend on making things take a really long time to crack. Nope. A system would be secure because a false state is physically unstable. It just couldn't exist. The time delay between making a decision and seeing its consequence, that would just vanish. And our ethics, our morality, would have to shift completely. From trying to control a process while it runs, to making absolutely sure the initial structure is perfectly aligned with our values before we let it collapse into a solution.
And if that wasn't mind-bending enough, this even reframes our understanding of physics. The paper suggests the speed of light might not be the ultimate speed limit after all. Instead, it could just be the unavoidable lag it takes for an instantaneous, atemporal decision to be expressed and translated into the space-time that we experience. Whoa!
And this brings us to the final, really provocative thought. If any of this is true, then maybe the solutions to our hardest problems, things like disease, poverty, ignorance, maybe they aren't things we have to build or discover over time. Maybe they already exist as latent possibilities, just waiting for us to find the right structural alignment to make them real.
The paper ends on this beautiful, almost poetic line. It suggests that the ultimate goal of computation isn't really to get an answer, but to reach a state of perfect internal consistency. A structure so coherent it doesn't need to compute anymore. It just is. What a truly mind-bending conclusion.